so here we've got a statics problem again. So we've got this girder hanging from a hook. We're assuming that everything's stationary, that the girder is just literally hanging from the hook and not moving. So the hook is our point of reference. We've got an upward force here acting from the crane cable, and then we've got a force pulling this way and a force pulling this way through these two cables here that are supporting the girder, and those forces are all acting on this hook. This hook is stationary, so as a result of that we know that everything's in equilibrium. All the forces acting on this hook must give a resultant force of 0. So when you take into account all the forces acting on the hook, the resultant force acting on the hook must be 0. Okay, so that's our starting point. So there's two different ways of doing this problem. I've shown you one already. Here's the second way. This way is a little bit more complicated. So this way, we're going to resolve the forces into horizontal and vertical components. Now, we don't need to do that for this force, but we do for these two, okay? So thinking about T2, first of all, T2 has two components. It's got a horizontal component in this direction, like that, and it's got a vertical component that acts this way, like that, okay? Now, there's a couple of different ways you could do this, but the way I like to do it is I like to take this horizontal component here and make it into a vector triangle by joining it to the vertical component. So what we're saying here is, there's the horizontal component, we've just translated it down here, made it into a vector triangle. So we've got the vertical component of T2, the horizontal component of T2, we join them head to tail, and then the resultant force is the hypotenuse of that triangle, okay? So that's the resultant force of the vertical and the horizontal components of T2. So to work out the vertical component of T2, okay, all you need to do now is use the 60-degree angle, and we're going to use cos to work that one out, because this is your hypotenuse, this is your adjacent, and this is your opposite. To work out the horizontal component of T2, we've got the hypotenuse, we need to work out the opposite to this angle, so we're going to use sine theta. Okay, now the same thing goes for T1. In this case, you've got the horizontal component of T1 acting that way, okay, and then you've got the vertical component of T1 acting along the same line as the vertical component of T2. So again, we're going to use this angle here. For T1, it's the hypotenuse. If we want to work out the horizontal component, that's the opposite, so we're going to use sine theta, sine of that angle. If we want to work out the vertical component of T1, it's the adjacent, so we're going to use cos of 30 to work that one out. Okay, so hopefully that makes sense. So what we need to do now is we need to think about this. All the vertical forces must add up to 0, because we know that there's no resultant force on this hook. So the way we're going to do this then, we're going to say that there are basically 3 vertical forces. There's the 16.5 kilonewton force acting upwards, and then there's the vertical component of T1 and the vertical component of T2, both acting along the same line here, and they're acting downwards. And we know that when we take that force and these forces together, they must equal 0. So let's make an equation for that. So first of all, T1 cos 30, that gives us the vertical component of T1, plus T2 cos 60. So that's T2 cos of 60, that gives us the adjacent of this triangle here. That gives us the vertical component of T2, and they're acting in the same direction, so we're adding them together. Now, if we take away the 16.5 kilonewton force, because that's in the opposite direction, then that must equal 0, because there's no resultant force in the vertical direction. So there's our first equation. Second equation, we now need to consider the forces that are acting horizontally. So if we just ignore that, because I drew that originally to try and show something, but I've moved that down here. So if we try and think now about the horizontal forces, now it might look a little bit odd because we're working out these horizontal forces here, okay, which is away from the hook, but it doesn't matter, okay? I'll show you how that doesn't matter in a minute. So let's think about them as they are here for a minute. So the horizontal component of T2, take away the horizontal component of T1, must equal 0, okay, because they're acting in opposite directions and they're the only horizontal forces. And we know that the resultant force on this hook is 0. So first of all, T1, I'm going to use sine because this is the opposite. Sine 30, take away T2 sine 60. So that works out the opposite, this horizontal component of T2 must equal 0. Okay. Now, as I said, you might think it's a bit odd because we're working those out here. If we were to consider them at the hook point, I should have left this arrow in place. Okay, so if we consider it here, like that, what you'll notice is if that's 60, okay, this angle here must be 30, okay? And then so that's the horizontal component of T2. If this angle here is 30, that angle there must be 60, and that's the horizontal component of T1. So we could write this equation in a different way. Now that we're using this 30-degree angle, this horizontal component of T2 is going to be, let's think about T1 first. This horizontal component of T1 here is T1, that's the vertical component, T1 cos 60 because this is the adjacent now. So T1 cos 60. And this horizontal component here of T2 is T2 cos 30. Okay, now you might think, hang on, we wrote sine 60 there and cos 30 here. Well, if you put that into your calculator, cos 30 is equal to 0.866. So that's 0.866. Okay, and if you do sine of 60, you get 0.866. Okay, so cos 30, sine 60, same thing. It's two different ways of working out the horizontal component of T2. And you'll find with cos 60, that gives you 0.5. Sine of 30 gives you 0.5. So although it appears that we've got different equations for the horizontal component of T2, depending on whether we consider them at this, whether we translate it down here for this vector triangle or we consider it at the hook, they actually give the same value. Okay, so now we've established that, we actually want to just get on now with working out what T1 and T2 are. So we've got some simultaneous equations here. We need to look, first of all, is there a common coefficient? And there isn't. So what we're going to need to do is we're going to need to get a common coefficient. So the easiest way to do that is multiply this one by sine 30 and multiply this one by cos of 30. Okay, so if you do that, we're going to take these equations and write them down here. Okay, so this first equation, so we'll call this equation 1 and we'll call this equation 2. Equation 1 will become cos 30 times sine 30 gives you 0.433. Okay, so if you take cos of 30, don't forget to put the bracket on the end, multiply it by sine of 30, you're going to get 0.433. Okay, so sine 30 times cos 30. Cos 30 times sine 30 here will also give you 0.433, and that's both for T1. Okay, so that's equation 2. So if we multiply cos of 60 now by sine of 30, we're going to get 0.25. Okay, and then if we multiply, have I done this right? Yes. If we multiply now sine of 60 by cos of 30, we're going to get 0.75. So that's minus 0.75 T2. Okay, for that one. And then we mustn't forget this function, this component here, sorry. So 16.5 multiplied by sine 30. And that's going to give you 8.25, and it's minus 8.25. And that equals 0. That equals 0. Okay, so what we're going to do now is we're going to take away equation 2 from equation 1. So if we take away, if we work that out under here, 0.433 T1, take away 0.433 1, that's obviously going to just cancel out, okay? If we take away 0.75 from, if we minus 0.75 from 0.25, we take those away, you're going to get just 1. So that's going to be T2, okay? Because essentially you are adding 0.75 to 0.25. And then we're taking away 0 from the rest of the equation. Then there's no factor here to take away, so that's just going to be 8.25 equals 0. So we've taken this equation away from this equation. Then if we rearrange this, we're going to get T2 equals 8.25 newtons. Okay, so now we've got T2. And then finally, all we need to do is substitute T2 back into one of the equations, whichever one we want, in order to get T1. Probably easier to do this one because it's got less aspects to it. So if I come over here to do this, if I do that here, so we're going to get T1 sine of 30, and I'm going to take that over the other side, is equal to 8.25 sine of 60. So T1 is equal to, so what we're going to do is we're going to do 8.25 sine 60 over, sine 30. So 8.25 sine of 60 all over sine of 30. Whoops, forgot to put the bracket in. So that's going to give you 14.3. So 14.3 newtons. The eagle-eyed amongst you will have spotted the deliberate mistake I made, which was that obviously this is kilonewtons and this is kilonewtons, not newtons. All right, so there you go. That's everything sorted.